today, and the questions is regarding the stealing from a house and collecting the money. Okay, so question, you can see you are a professional robber and planning to rob a house along a street. Each house has a certain amount of money attached. The only constant stopping you from robbing each of them is adjacent house and have a security system connected. So it will automatically contact the police if the adjacent houses were broken into the same night. So this is the constant. So you do not have to stole from a consecutive house, adjacent house, right? And because it is a system that has been made, like a security system has been made, so that it will automatically connect to the police, and you cannot do the house robbing. Okay, so given an integer array nums representing the amount of money of each house, and we have to return the maximum amount of money you can rob tonight without alerting the police. If the police alerting, you will fail. So let's see the example one, and you can see that we have number of houses, right? This is the nums and this is the number of houses, and output getting 4. Why? Because if we'll start with the first one, right, the first house, starting robbing, right? So what will happen from robbing first house? We will get 1 as a money, right? And when we talk about we cannot do for the second, so we will not go to the second house, we will move to the third house, right? And that's why we have the money 3. Let's understand one more time. Give me 1 minute. Okay, so let's see, we have 3 consecutive house, right? This house, this is house 1, okay, this is house 2, right? This is house 2, and this is house 3, okay, house 3. So if you are going to do robbing, right? So if you will start from here, right, this house, if you will start from this house, you cannot rob this house again. Okay, you have to move to next house. This is the meaning of the question, right? If you rob this house, means the police will get alert, and you will get you will fail there, you can say, right? So the money we have here is what? 1 in the house, this is 2, right? But we are not going to collect. This is 3, correct? And the next house that we don't want, right, to rob, because this is also consecutive, we cannot do here. And next house we don't have. So money will come from what? This house 1, what will come 1, and from house 3 it will come 3. So this is become 4. Okay, and similarly for this house, if robber will start from 2, then he will count what? 9, and then 1. So 1 2 2 9 and 1, what happened? It is 12, right? So in this way we have to rob, and then we will move to the next level. Okay, next house. Now our professional robber is our professional robber is in for a trade, and they have a buffet of a house available for them to rob. Okay, so technically they can rob any of the houses, right? They can rob any of the house on the street. However, the alarm companies are smart enough to catch any robber red-handed under certain conditions, right? That we know. And if we were no alarms in the house, obviously the robber would rob every house and make the most money. But this is not the condition, right? However, now they have a lot of choices to make, and let's look at a few houses on the street, the different choices of our robber can make, and and how those choices will affect the heist. Okay, so figure 1, it is saying that an example showing the robber making the optimal choices to obtain the most money. So in this example, the robber ended up making 600, which is maximum they can make for this series of house. Let's take another set of choices that robber can make where they will not make the maximum amount. Okay, so first in this example, what happening, he has started from here, right, this house, right, and he has got what? 100, right? Now coming to the next one, he cannot move, right? That's why he is going to the, he has escaped this house, he has escaped this house, he is not going to do that, and he will do from another house, and he will get consecutive money, right? And now he is not getting here, but he is getting here, right? So now if we'll calculate, first house is getting 100, now 400, and then 100, right? So total, if you'll see that how much he is getting, right? 600, right? 600, yeah. So this is in the dollar, these are on the dollar, right? So he's become a king now of $6. So, and the in this figure you can see that the same example showing the robber making suboptimal choices, right? So in this case, the series of the choices that the robber made turn out to be less than optimal, and they ended up making paltry to 50. A series of choice if essentially gives us a subset of choice from the original list, and we will make the choice in such a way that the overall profit is maximized, right? So if the robber is not going to he is thinking that the starting is not good, right? So he want to start with the second one, right? So he got 50, initially he got 50. Next he cannot do that, right? So he is going to do next one. Here he got what, 200. Next he cannot do that, right? So he can rob only two houses. In this case he got $250, right? That is not optimal, right? That is not optimal. As you can see that the robber is very unhappy that he has started from the second house. He is not happy now, right? So there is no greedy way to deciding if the robber should rob a house or not. The best greedy strategy may be to check the neighboring house and only rob a house if it gives them more money than the neighboring combined, right? That might be a sound greedy strategy, correct? So however, by doing so, the robber may miss out on making the maximum profit. So let's look at the example that depicting the failure of greedy strategy on the same example, right? So in this example you could argue that after the robber decided to rob the third house, they could go back and rob the first one as well. In this case we will give us the optimal answer. However, that decision is still local in that we just consider three houses at a time, right? What we'll do here, we'll start from the first house, right? And sorry, we will not start from the first house, correct? And second house, he is going to start with the third house, okay, and the last house, okay, and he's not considering this house. So in this case he got what, first 400 and then the last one 100. So he got $500, right? So still he is unhappy. So what we need to try what we need is to try all the possible, and which one gives us the robber the optimal loot, right? So the there is many approaches, various approaches we have, in which we can see that the recursion with the memorization, dynamic programming, and optimized dynamic programming, okay? So these are the approaches we have. So if we talk about the recursion with the memorization, right? So the easiest approach here is to try all the possible combinations, right? This is for the house robbing, okay? So house choice. So try all the possible combination for house choice, then use a combination that gives a maximum amount of money to robber. We do this because there is no plausible greedy strategy that we will use to decide if the robber should rob a house or not, right? What are you saying? So this is the easiest approach, and we have to try all the possible combinations of the house, and then we will combine so then we will use the combination that gives the maximum amount of the money to the robber. So we do this because there is no plausible greedy strategy, and that we can use to decide if the robber should get the particular house or not. we rely on our good friend recursion, correct? So whenever we have a choice involved in the solving a problem, technically a robber can come back and rob a house that they previously rejected. However, since we are trying all the options, we will not go back and rob an unrobbed house, since that scenario will be converted into different recursive path. So the basic choice that we will make is whether the rob the house, current house or not. If the robber decides to rob the house, current house, they have to skip the next house. Otherwise, they can evaluate the same choice on the next house and to rob next, to rob or not. So the problem is saying that to approach a problem recursively, we need to make sure that it can be broken down into subproblem. Additionally, we need to ensure that the optimal solution to this subproblem can be used to form the solution to main problem. So let's see how we can divide this problem into smaller recursive problem. So let's say that we have a function called rob from, which we will use to solve the problem. The only input this function take is an index position. This position essentially represent a suffix in the array which we the robber have yet to scan. Essentially, the position indicates that the robber has yet to scan houses position to n, where n represents the total number of houses. Naturally, the answer is our problem would be the function called rob0, which means scan all the houses and return the maximum profit. Now let's think about rob I. For a moment, this simply represents a sub-array or a suffix from the main array. We can think about this as a smaller maximum profit problem in itself, and can't we? So a suffix of an initial set of houses simply means a smaller set of houses that the robber has to consider. We will be working with the assumption that the function call rob from I, the robber has to maximize their profit from n houses, right? So at each step the robber has two options, right? If he chooses to rob the current house, he will have to skip the next house in the list by moving to the two steps forward. If he chooses not to rob the current house, he can simply move to the next house in the list. So let's see this mathematically. rob rob from I. So this is the I, you can say house. So how do we will do that? So I plus 1, we have to find the maximum between the I plus 1 and I plus 2 plus num of I, the previous one, right? So this will give the maximum and which will come to rob, right? Recursion tree and memorization. Now we have an idea about the recursion recursion structure of our problem. So let's look at the recursion tree and which will be formed. So this is important so that we can determine if we have repeating sub problems in which we can use memorization and caching to reduce the overall solution complexity. So if we'll talk about the overlapping subproblem in the recursion tree, as we can see that the recursion tree, right, we have repeatedly subproblem and mark the same color. So repeating node in the tree represent the entire sub calculation has to be repeated, which is computationally expensive. Hence we cache the already computed result so that we don't need to recalculate the maximum profit for previous seen sub problem, right? So let's see, we are starting from 0, first house, right? Rob from 0, then he can move to either 1 or 2, right? Either he want to move next rob from 1 or rob from 2, correct? If he is going to rob 1, means he has two options now, either he will rob 2 or 3, right? Similarly for 2 we have 3 and 4. But if you'll see that if he has traversed this node, right? So if he has started from here, he has started the first, then he want to go to 2 or 3, right? He wants to 2 or 3. 2 is already calculated, right? 2 is already calculated, and that's why when he is trying to go in this approach, means we have already calculated, right? So we can get from the memory, we can get from the cache. Similarly for the 3, it is already calculated, and we do not need to do. So in this case for 2 and 3, you can see that we can cache, we have already cached the data, and we do not need to recalculate, right, in the sub problem. And similarly for 4, if there is further houses are there, right? Now let's formalize the idea concretely in the algorithm section. So what we can see that we have to define a function, that is a rob function, which takes the index of the house that the robber currently has to examine. And also this function takes num of array which is required during the calculations. At each step of the recursive call, robber has two options. He can either rob the house or not. So if a robber choose to rob the house, right, he have to skip the next house by I plus 2, okay, if he is trying to do. So if the answer here would be whatever is returned by I plus 2 then num, right, in addition to the amount of the robber will get by robbing the current house num of I. So this is the current house num of I, and this will come from he will skip the next house and going to the next house, right? Otherwise he will simply move on to the next door and return whatever profit he will make from the subproblem, that is I plus 1, okay? So we need to find cache, return the maximum of these two options of each step, and we will do fourth option, rob 0 nums will give the answer of the entire subproblem. So let's see the coding sections, right? So we have to define a memo that will store our cache data, right? The calculated steps will have all the data here. So we have a function that will take nums, right, and we will initialize our memory of the what data, right? So this is nums, right, and we are initializing with 100 as a size of the array. Now we will do arrays.fill this dot memo, and we will do -1 to fill the initial value of the array, and we are filling the initial value, non-calculated recursion for, right? Return this dot rob from 0 comma num, and this will give you result, right? Result from which this will return as a recursive. This is a recursive function rob from that we will discuss here, and this is the final data we will resolve, because we will start from first house 0 and nums, right? So if int I and nums we are passing in the rob house, this is the recursive function, right, and they will calculate multiple times, right? So base cases is what? If I is greater than or equal to num, means we are at the no more houses left to examine, correct? And that's why we will return 0 here, correct? If I is greater than or equal to num, right, num length, right, means we are left and there is no examine to left, okay? We do not have houses to left, okay? Next, if this dot memo is greater than -1, it means the initial value don't have, we have already calculated, means we will return that value. Next, the recursive relation evaluation to get the optimal answer is that math.max, in which we will pass I plus 1 for the current one, and then I plus 2 for the we are skipping this one, okay, and num of I, okay. This is the nums, right? This is the num I plus 1 nums we will passing, and I plus 2 nums, right? But we are passing the current value num of I, okay. So which one is the max? This one, these two, this one between this, and that will come as an answer. I will store on the memo of I, and finally we will return answer. Sorry. So complexity analysis, if we'll go, so both time complexity and space complexity will remain same O of n, because in the time complexity, since we process at most n recursive call, right, you can see here at the line number 24, you can see that we are doing so. So thanks to caching, and during each of these calls we make an O of 1 computation, which is simply making two other recursive call, finding their maximum and populating the cache based on that, right? So if we are calculating and we are storing on the memo, right, and that's why we are taking the assumption that it's taking the O of 1 computation for each node, and that's why we have total n nodes. That's why we are getting O of n. But if we talk about the space complexity, so we have taken the memory, right, to cache the data, and that's why which is occupied by cache and also by the recursion stack, right? We are doing recursion as well as we are storing the caching. That's why the space remains same for O of n, the number of houses we have, so O of n. Now coming to dynamic programming, right? The idea here is the same as before examining the instead of following a recursive approach. We will be sticking with a tabular approach, right? And the recursion approach may run into problem, right, or trouble when the recursion stack grows too large. It may also run into trouble because for every recursive call, right, the compiler must do additional work to maintain the call stack variable, or you can say functional variable, which result in unwanted overhead. The dynamic programming approach is simply a tabular formation of ideas presented above that we've seen, right? The cache we had before will still exist in the approach. The cache we had before will still exist in this approach, but instead of calling it a cache, we will refer to it as our dynamic programming table. So every DP subproblem, every DP problem, right, solution has a table, correct, that we populate starting with the base case or a simplest of the cases for which we still know the answer, that is for our problem. We know that in the presence of house, the robber will make zero profit. Similarly, if there is just one house left to rob, the robber will rob that house and will be maximize the profit, right? So we start with the populating the dynamic programming table with the initial value and then build the table in the bottom of fashion, which is essential for the solution. So let's look at this algorithm and we'll see the problem. Okay. So algorithm is saying that we will define a table which will be used to store the result of the sub problem. So let's call this problem as max robbed amount, and max robbed amount is an array, is the same value that would be returned by the recurse function in the previous section. So we set max rob of n to 0, which since this means the robber doesn't have any house left to rob, thus the 0 profit. Additionally, we set max rob function n-1 to num n-1, right, n-1 to nums of n-1, because this is the case, right? This is the case because in this case there is only one house to rob, where is the last house. Robbing it L to maximize profit. So we will iterate from n-2 to 0, and we will set a maximum rob amount I equal to the max between I plus 1 and I plus 2 plus num, right? The same function. Note that this is the same as recursive formulation in the previous solution, right? The only difference is that we have already calculated the solution to the subproblem, and we simply reuse the function of one time when calculating the solution to the main problem. We return the value max row amount I, right? So let's see the program here. As you can see here, what we have a problem n equal to nums dot length, right? And we will take n, if n equal to 0 means we will have to return 0 because we are handling empty array case, right? So we will take row amount here, right? Row amount, and this will be our what, length plus 1, and then we will take what, row amount n equal to 0, n minus 1, num minus 1, right? And then we will calculate the recursion, and then we will do I plus 1 and I plus 2, whatever the maximum will come, right, for the with the current value, that will come to the max row amount, and we will return final value as we do for the as we are doing for the recursion, right? So only base case initialization we have to take care, that we will say n max row amount n equal to 0 and n minus 1 equal to n minus rob num of n minus 1, and we'll start from n minus 2 to 0. We will start from the last bottom, right? Actually this is bottom up, and that's why we are setting this value. So complexity will remain same because we are looping n minus 2 to 0 index, and we are using what the n nodes value, right? So another program that we will do for the optimization problem, that this is the best approach, and we will see that complexity of space is of n, right? So this is the exact same solution as previous one, with the exception that we will be optimizing the space complexity here. Let's look at the recursion relation again to see where we can reduce the amount of space used. So if we will take a rob of I, rob from I, the max between I plus 1 and I plus 2 plus num of I, right? Between these and between these, right? So whatever will come, that will be our row of I. So to calculate the current value, we just need to rely on the next two consecutive value, that is recursive call, correct? So porting this idea over to our dynamic programming solution, we see that in order to calculate the value at the current index in the dynamic programming, we simply need to know the next two value, that is max row amount I plus 1 and max row amount I plus 2. So in this, and we will return the value of max row amount 0. Instead of keeping an entire table for storing these cached value, we can get by simply keep track of next two values. Let's say this more concretely in the algorithm section. So the algorithm is that we will make use of two variable here, the rob next and rob next plus 1, which at any point we will represent the optimal solution for the max row amount I plus 1 and max row amount I plus 2. Okay, we are taking actually two variables, rob next and rob next plus, and what we'll do that we will take optimal solution. For that, what we have to do, we have to take max row amount I plus 1 and max row I plus 2. So these two values that we need to calculate calculate the current value, we set rob next value to 0, since this means the robber doesn't have any houses to left, thus 0 profit. Additionally, we set rob next to num n minus 1, because in this case there is only one house to rob, which is the last house. Robbing it will yield the maximum profit. Note, we are assuming that rob next plus 1 is the value of rob maximum value, right? That's value will come to what? Max rob amount of n, and rob next is a max rob n minus 1, correct? So these things we have to take care. Third step will saying that we will iterate from n minus 2 down to 0. We'll set current equal to max rob next. Then what we'll do, we'll start with rob next plus 1 and plus the current value, right? And this will store to the current. So note that this is the same as the dynamic programming solution, except we are making use of variable, not entry from the table. We are setting robs next plus 1 and equal to rob next. So this will set the value. Then rob next equal to current we will set and update the two variable is important as we iterate down to 0. So we will return the value rob next. Let's see the coding section here. We will start n equal to what? Nums dot length, right? And then this is our empty array case. This is the base case. Then rob next, and we'll take rob next plus 1, two variable we are taking here, right? Now what we have to take in the base case, rob next plus is 0 and rob next is what? N minus 1, the last one. Okay, so the DP table calculation, note we are using any table here to store value. Okay, just two variable we will suffice. Okay, we'll start from n minus 2, the last, and then we'll come to 0, right? And I minus minus. This is called, sometimes some people also call bottom up, right? So int current we will take max, right? In the max we will take rob next and rob next plus 1 plus num of I. Okay, so rob next plus 1 and the plus num of I, this is the current value. We'll take this current sum, we can say, this will come to what? On the current, correct? And then rob next plus will update to rob next. Rob next plus is rob next, we are updating the variables, and then rob next is what? The current that we have calculated, and finally we will return rob next. And that's why we are getting the time complexity element same, but the space complexity is what? We are not using table to store value. Actually we are using two variables to swap, you can say, a suffice, we can say, for the calculation, and that's why we are getting the updated, right? Only what you have to do, take two variables, and that we have to initialize 0 and -1. But when we are getting the current value, that we have to take care of the rob next, and the previous we have to store on rob next plus, because we are using this variable here, right? We are using this variable here, and rob next value should have your what? The previous current, and that should be here, in which the previous current and the robbing next plus the previous value, whatever is the maximum, that will choose in the current, and that will need to update each time, and we will return that. So I think that's, we have already completed all the approaches, but for the follow-up questions, if you have completed the previous problem, so you can follow up these questions. I will send you into the link, right, if you need, or you can go through that. So thank you so much for liking this, right, and please subscribe Expert Fund.